Okay, Gilyoung, would you say something just so everybody can confirm that they can see and hear you, please?
Is that?
Yeah, this is good. Okay. Any technical problems, please?
One sec. I mean, I would like to share the link of the slides because I think it's much easier to. Hold on, maybe it's not the full link. Sorry.
Okay, good. And let me encourage you to also post those to Discord, please.
I see. Yeah.
But yeah, great.
Where should I do it in the?
You can put it on Discord. You just give us the link.
In the which part of the Discord should I put in? Put the link on.
What did you say, Padma? Okay. So,
chat about talks. I posted there. Don't worry.
Oh, okay.
Okay.
Okay. Thank you very much.
Okay. All right. Great. Are you ready to go then?
Yeah, I am. I'm ready.
Okay. Great. So our first talk of the morning is going to be given by Gilyoung Cheong of the University of Michigan, and he's going to be speaking on Cohen-Lenstra distributions given by p-adic matrices. Please.
Yeah, thank you very much for invitation and thanks very much for coming. Today I'll talk about some sort of basic problems about the distribution of co-kernels of random matrices over ZP. Those are going to be square matrices and I'm going to use Haar measure. And I'll tell you where some of this motivation came from. And I also put the sort of the journal information just because I'm a graduate student. I'm sort of anxious about like being wrong all the time. So it's just hopefully this gives you some sort of credibility and relaxing moment. So this is a joint work with Yifeng Huang, and I believe he's here too. So let me start by, okay, so yeah, I think it's not important. So the motivation comes from somewhat difficult problem in number theory, where you first think about imaginary quadratic field. So Q joins square root of D, where D is a square-free negative integer. And you can think about the class group of this field, or field extension of Q. And this is always finite abelian group, so therefore it's supported on finitely many primes or maximal ideals. You can think about this following exact sequence where you start from the non-zero element from the field where that is supported by these specific primes that you pick, and then you think about this free abelian group generated by these primes, and then you think about how to you think about surjecting to the class group because these are some generators you picked, which is that's going to be surjective. So in this case, because this K is imaginary, the field is imaginary quadratic, it turns out that the first group has rank n and the second group automatically has rank n. So you can think of this as an exact sequence where you have z to the n going to z to the n, and then going to the co-kernel will be the class group. So let's take tensor product with ZP, the p-adic integers, and then you get the following exact sequence because tensor product is right exact. And CLK is a finite abelian group. So you get now the p part of the class group of a quadratic imaginary field that you start with as the co-kernel of a linear map from ZP to the n to ZP to the n. So you can think of this as a n by n matrices or matrix over P, ZP. So then if you start to wonder about, okay, so like if you pick a random imaginary quadratic integer where you have to think about what random means, but say that you have a notion for it, then you can ask what is the probability that its P part for, say, odd prime P is a specific finite abelian P group. So as sort of heuristic, so I mean, you can think of it as, you can instead think about, okay, well, it's going to be some sort of co-kernel of ZP to the n to ZP to the n, where of course n could be dependent on which class group that you start with, but say you have a large enough n, and then you can wonder, maybe you can sort of like, maybe this problem's too hard, maybe you can think about, you know, some easier notion of randomness of these matrices, and then see whether or not see what's the probability that you get certain kinds of co-kernel, because your class group will appear as a co-kernel. So it's a heuristic, not trying to attack this difficult problem. So Friedman and Washington did that in 1989. So they took random matrices, random n by n matrix. That's and then they took it into with respect to Haar measure, and then for fixed finite abelian P group H, the probability that this co-kernel of this random matrix is isomorphic to H. As n goes infinity, it converges to some number, and this number is a positive number. But what's interesting is that it's inversely proportional to the size of the automorphism group of H. Okay, that Z just refers to the fact that we're thinking about abelian groups, Z modules, in the notation for automorphism group. And then you have some normalizing factor, whatever that is. This was interesting because even before sort of this heuristic came up, so Cohen-Lenstra in 1984, so it's before 1989, I think. So basically for odd prime P, so these notations may not matter too much. So it is just conjecturing that if you have a random imaginary quadratic field, the P part of your class group, but they conjecture that it's going to be exactly that number. I see something on the chat. Maybe there was a. Okay, I see. Yeah. Yeah. I mean, in any case, yeah. I hope you have access to the slides so that you can go back and forth if you want. Okay, that's what this means. I mean, it's just basically like other parts are notations. So I don't think that's important. And also there is a. I mean, I guess this is a lot of times this is true in number theory, where you start with the problem about Z, and then you sort of get stuck, and then you sort of give up and try to look at FQT instead. You know, hoping that maybe some structure about polynomials or algebraic geometry might help. Okay, so people did that as well. So they replaced Z with FQT. So then your Q should be replaced with FQ round bracket T. And then you'll have to pick some D as a polynomial. So it's going to be monic square free polynomial. But then for some technical reason, Q is odd, and your degree of D has to be odd as well, has to be greater than or equal to 3. And in this case, if you look at sort of geometric world, where you think about geometrically reducible smooth projective curve C over FQ, which basically means for the affine case, it's going to be y squared is equal to d of t for the affine part. but then you have to do some projectivization in a careful way. But that one, that curve has 1 point over infinity. This is something now over P1, and that somehow has to correspond to the imaginary quadratic field, which I don't know. For me it kind of I don't want to offend people. For me, this sounds like sort of a made up analog, but I don't know. But this is somehow what people believe, that this condition that we have only 1 point, not 2 point over infinity, is the right analog for imaginary quadratic field. But you can disagree that this might be natural to you. So I don't. But yeah, in this case, in any case, it turns out that for any odd prime that does not divide Q, we can present the class group of this field K, which is now a degree 2 field extension of FQ round bracket T, using the following short exact sequence: ZP to the 2G, and then ZP to the 2G, and then you get the P part of the class group as the co-kernel, where now G is going to be the degree of that polynomial D of T we picked, -1 divided by 2. And that's going to be exactly the genus of the smooth projective curve that we were talking about before. And in this case, the way you pick this matrix is going to be some matrix minus identity, where the matrix A itself is invertible. Like invertible. So GLN. Something in the GLN. So then now you can sort of think about, okay, so maybe this problem's still hard. So then can we think about sort of heuristic, where you think about a random matrix of GLN in GLN ZP, and then sort of do the same type of calculation. And Friedman and Washington did that in the same paper in 1989, where now like GLN is a subset of mat n, where what I mean by mat n is n by n matrices. So you can restrict the Haar measure that you have on mat n, and then but then the total measure is not going to be 1, so you normalize so that you get total measure 1. And then with that measure, as n goes to infinity, if you take the co-kernel of the A minus the identity, sorry, the IN means identity, yeah, n by n, identity matrix. If you take the co-kernel of that and ask whether what's the probability that it is isomorphic to the fixed finite abelian group, finite abelian P group H, then you get exactly the same probability, which was suggested by the problem of Cohen-Lenstra. So and again, this sort of what I'm writing here was a conjecture by Freeman and not Washington, but Washington, where they actually asked a similar type of conjecture for this function field case. But unlike this number field case, this function field Cohen-Lenstra, I mean, there's a huge progress made by Ellenberg, Venkatesh, and Westerland when Q is large enough. And the exact formulation for me right now is like, it's a little hairy for me to remember, but it's a lot more satisfactory and quantitative than what we knew about the number field case. And so I mean, so Ivan and I were not trying to do this, like resolve this, sort of, I don't know, maybe Fields medal winning type of questions about this distribution of class groups, but we were still wondering about, so if you look at this result and then the previous result, I mean, these about Friedman and Washington, these are just statements about matrices and its measure. And of course, these are related to this sort of this problem about class group. Sorry, problem about distribution of P part of the class group. But they're just statement about matrices, and we're interested in why sort of we're getting the same answer. So that's sort of the whether or not we're using n-bio matrices or invertible matrices. So that was our motivation for this question. But now we're sort of, I don't know whether or not we're like, I mean, now I think we're sort of out of number theory in some sense. But like now we're just like thinking about p-adic matrices. But like maybe p-adic matrices is number theoretic enough for you, then it's still number theory. But now it's sort of, for us, it's sort of a pure mathematical, I don't even know. Like maybe it's a combinatorics, maybe it's a linear algebra, but now it's just now we're only thinking about p-adic matrices. Okay, so what we did is that we sort of generalized these two results as a sort of a uniform result, and then that includes more cases. Okay, so what is our statement? Our statement is the following. So our statement is that, like, suppose that you pick some finitely many monic polynomials over Zt with univariate, and suppose that these are if you reduce mod p, these are irreducible polynomials over finite fields. Something is missing here. We want this to be distinct irreducible polynomials. That's the assumption. That's our assumption. And suppose that one of the polynomial has a degree 1. Okay. So then for any finite abelian P group H, then what we're requiring for probability is that we require the co-kernel of P1 of A. So you have a square matrix A, and then you apply the polynomial P1, and then take the co-kernel. And then we want that co-kernel to be 0, and then all the other co-kernels to be 0 except that degree 1 polynomial. For that, we just specify that co-kernel to be isomorphic to the given finite abelian group H. Then as n go to infinity, we get this sort of weird expression that looks kind of like Cohen-Lenstra. So notice that this, so when r is equal to 1, okay, then notice that it is exactly the same thing as the what we get for previous result about just the first result about random matrices over Zp. And when r is equal to 2, this also sorry, I do have to specify what I mean by these p's. So when r is equal to 1, we actually restrict to the previous result about Friedman and Washington. I guess I don't have to go back to the page because you guys have the slides. I totally forgot. I was anxious about this. But then, and then you have to pick p of 1 to be t. When r is equal to 2, when you take p of 1 to be t and then p of 2 to be t minus 1, our theorem actually reduces to Friedman and Washington's results about GL and ZP. You have to think a little bit about this, but that's what happens. What's interesting about our result, sort of aesthetically, is the following. It's just that if you look at the result, you look at these polynomials. We start with ZP polynomials, but then really, what we really are sort of emphasizing here is that these are going to be irreducible polynomials when you reduce to mod p. So if you like algebraic geometry, these are going to be the sort of close points on the affine line over FP. And somehow what our results is suggesting that there's some sort of independence going on with respect to each point. Okay, and this is sort of a theme that actually pops up in many places. So I hope you're interested when you look at this stuff. Yeah, these polynomials are distinct. There's a typo I didn't. They're distinct mod p. Yes. Okay, so are there any questions so far about the result or anything? You can talk. I mean, it's a totally legitimate question why you guys are doing this, but hopefully that was enough motivation for you.
So you sort of taking the two theorems and putting them, taking some hybrid analog where you have.
Yeah.
Can you can you go? So you said this specialization P1 is T, P2 is T minus 1 recovers Friedman-Washington results. Do you?
Yeah, the second one about the GLN.
About the GLN. Can you also recover part of Ellenberg? Venkatesh,
yes, there is no way. Yeah, no. This is just about the theorem about matrices, and what Ellenberg, Venkatesh, and Westerlin prove are really the information about the actual class group of some field extension of FQ round bracket T. So yeah. So sadly, no. Yeah. Thanks for the question.
Thank you.
Yeah.
Yeah, please ask lots of questions. We hope to be more interaction.
Okay, so if there are no more questions about the result itself, I will describe how we resolve this problem, and I think that is itself interesting in the sense that what I'm gonna do is to explain how to reduce this problem to a problem about some combinatorial problems of matrices over finite field FP. Okay, and then maybe if I have enough time, I'll explain the how to actually resolve that combinatorial result. But that turned out to be already known. So we'll go through that. So so here, so this is sort of a similar setting that we have finite element ZP polynomials, and then we want to match with some finite element P groups. So what it's basically saying is that when you're thinking about matrices over ZP, or at least in my case, when I was thinking about this, I thought it was sort of too difficult to look at ZP matrices. So this is a lemma that actually makes you not think about ZP matrices. You can just think about some matrices over Z mod P to the large N, as long as your power of P to the minus N minus 1 annihilates all these finite abelian P groups. These are finite abelian P groups, so therefore there is such an N. Okay. And for N is equal to 1 is actually quite interesting. This is something that we overlooked for a while. Well, N is equal to 1, it says that it is exactly that when HJs are equal to 0. And what's really great about that is that when N is equal to 1, Z mod P to the N is a field. That's when we have the finite field. And that is actually quite important in our work. But in any case, for the general case to prove this lemma, it's just a simple application of symmetric normal forms, because ZP is a p-adic. Okay, so keep that lemma in mind. And again, yes, this is going to be a reduction to combinatorial problem over FP, and then resolving that combinatorial problem. That would be the two parts of resolve how to resolve this main theorem. Okay, so now let's think about this reduction of the main theorem. And remember that for the main theorem, you can go back slides if you have access. You should have access to it. Otherwise, please ask. And we only fix one finite abelian P group H. Okay, and we fix n such that P to the n minus 1 is equal to P to the n minus 1 times H is equal to 0. So that we can just think about matrices over some finite ring. And then we have this PR that has monic in degree 1. Okay. What's really crucial for our work is a lemma given by Friedman and Washington, and I'm not going to state the exact computation. It's a bit of a mess, but what the lemma says is that for any given n by a matrix over finite field FP, you can exactly count the number of lifts that actually goes to the A bar, where the matrix over finite field that you start with the condition about the co-kernel after pushing with the P of R. So after the condition about co-kernel P of R of A being isomorphic to H with that, and you can count exactly how many number of lifts are there. And what's really important about this, the first property or lemma that we use is that P of R is degree 1. But I mean, but then this is some sort of heroic linear algebra. Like I try to generalize a lot and try to have some meaning behind it, but it's just given by some heroic linear algebra. And so the second point, just note that such matrix, if you have such a matrix, say that you have a lift such that co-kernel P of R of A is isomorphic to H. So that's the last condition that we needed for our theorem. This automatically satisfies when you actually now push down to the matrices over finite field. It has to be isomorphic to H mod PH. Yeah, it is pretty heroic. Yeah. Oh, sorry. Maybe somebody private chatted me, which I'm not gonna mention the name, but somebody told me that I like the notion of heroic linear algebra. But it's, yeah, there is such a thing. But anyways, so the last thing is it means just that. It just means that these two are FP vector spaces, and they just have the same FP dimensions. Okay, so then with this in mind, now you can compute. So okay, this is a little hairy to look at right away, I guess. So let's look at this. What's important about this. Can you see how I'm highlighting this or no? Okay, that's great. Yeah. What's important is this after Y. Okay. So maybe I'll highlight this like this. So what's important is that when you think about the co-kernel, and now we're over a finite field, its dimension is actually the same as the kernel. Okay. Because what is co-kernel? Co-kernel is target mod image, but then if you think about it, like domain and the target were the same thing. So therefore, because the domain mod image is the domain mod the kernel is the image, so therefore it's they have to be the same. So what do you call this? Rank nullity theorem or something like that? I forget this important stuff. But then if you think of this A as now let's go outside the undergraduate linear algebra. Let's go to a little bit more advanced undergraduate algebra or basic graduate algebra. Then now when you think of matrix, you think of it as a you can think of it as a how do you say this, a module, or you can think of it as giving a FPT module action on the vector space FP to the n. And so you can think of A bar as a module over FQT that has a finite cardinality or finite dimension over FP. So then you can think of its P torsion part, where you only look at the parts where it's supported by this polynomial P. And then you mod by P times that, and that exactly turned out to be the kernel. Okay. And saying that this co-kernel P A bar is 0 is same thing as now dimension of co-kernel P A bar is 0. That's also same thing as the dimension of all the way in the right hand side, which is like A bar P infinity over P A bar infinity is also 0. But by Nakayama lemma, that's actually same thing as saying that A bar P infinity is equal to 0. Okay, so that's why like we can make our left hand side our theorem into this quantity. And now as you look at it, now this is exactly in the realm of thinking about matrices over finite field, which is a lot simpler than thinking about matrices over p-adic integers. Okay, so that sort of this reduction somehow was the key component in our work. So yeah, questions? Somebody raised the hand, yeah. Or maybe that wasn't a question.
You can unmute yourself and ask a question if you want, if it's okay with the speaker.
Yeah, I'm totally fine. I don't have agenda to go through every slide. Yeah, it's fine. I'll give you like 2 seconds. If you're not speaking, then I'll just think that it's okay to go. Okay, I'll go. But feel free to ask. Okay. So what's next? Okay. So yeah. Let me think. Yeah, so how do we know how many of these things have, so the first one, so the first R minus 1 conditions, like I was more okay with, but the second condition was something that I got stuck with. So how can I specify the dimension of co-kernels of P of A bars? Okay, so but that's somehow already done by Cohen-Lenstra in 1989 or something. So we just like directly use their computation in our work. Yeah, I mean, this computation turned out to be also not that complicated. I mean, I actually went through it, but it wasn't obvious at the time. But we, as when we actually wrote this up, like we actually just used the property of this measure that they. And what's really important then at the end was that, so remember that in our statement of the theorem, we had some 1 over automorphisms everywhere. Okay, so that one somehow now we want to sort of like, but then if we solve problems about matrices over finite field, because they're basically FPT modules, so the answers that we're going to get are not likely have something to do with Z modules. They're going to be something to do with FPT modules. So this was some sort of worriness in the beginning, but that it turned out that these are sort of worries that don't really exist. So it turns out that if you have sort of finite abelian P group of say partition type lambda 1 through lambda L, it's going to be same thing as a it's automorphism size of the automorphism group, where you take it as a Z modules, is the same thing as the size of the size of the automorphisms of some of the corresponding looking P torsion FPT modules with of the type lambda 1 through lambda L. Okay, so this was sort of a, I mean, this was a sort of a simple work, but I mean simple lemma, but it was sort of important in our sort of reduction and translation of the problem. But then again, so it turned out that there was a result, or we proved that there was a result that actually has this feature in the finite field random matrix world. So and thanks to Nathan Kaplan, we realized that this result also appeared in the PhD thesis of Borrego. So the result says that, so now you start with finitely many distinct irreducible polynomials, and you think for each polynomial you associate this finite pj torsion module, meaning that if you multiply enough p's, this is going to get annihilated. Then you take the probability where you take the pj torsion of the FPT module given by the matrix A, and then you just require that's isomorphic to HJ. And then if you do that for each one of them, you get something very similar to Cohen-Lenstra result. Okay, so and this was sort of the key, and this actually resolved our previous case. And then the fact that this one over automorphism could be written as a Z as a quantity in the sense of Z modules, that was enough to resolve the theorem. Okay. How many minutes do I have? Is it like
you got a little bit over 20 minutes left.
Okay, that's great. Okay, so then I'll just go through how to do this, how to work on this combinatorial result, unless if anybody has questions. I think I'm actually doing well on time, given that I have 17 of the 27 pages. Okay, well, so again, this is the result about taking a matrix at random, n by n matrix at random over finite field FP, and then you look at the FPT module. It defines on FP to the n vector space, and then you sort of require this P1 torsion, P2 torsion, P3 torsion, etc., to the PR torsion, and then you compute the probability. That's what we're up to now. So this proof requires this a combinatorial technique called cycle index. And if you like combinatorics, and this usually appears in the sense of symmetric groups a lot, and then there was an analog for matrices. So it's going to be some sort of enumeration or some sort of generating function that we're going to cook up some sort of generating function, and then we're just going to play with it until we get some sort of result, the numerical result. So we define Z of mat n over GLN FP comma X, where this X means a lot of variables, okay? But to be this thing where you first start, you take the sum over n by a matrix over a finite field, and then for each matrix you cook up a monomial, okay? So when you cook up a monomial, what you do is that you just give formal variable for every p part that is non-zero, okay? And then so this monomial remembers this which isomorphism class that A belongs to as an FPT module, okay? And then you sum them up, sum these monomials up, and then you somehow normalize by the size of the GLN, not mat n, but GLN, okay? Somehow that turned out to be important. And yeah, so this notation A1FP just means the set of monically reducible polynomials. And of course for X, so these X subscripts are going to be formal variable for any non-zero finite p torsion modules. But when you have 0, you define that to be 1. Okay. So yeah, like I said, these monomials are going to precisely record the information about the isomorphism class of each matrix as an FPT module. So in other words, if you have two matrices, they're going to be similar matrices if and only if these monomials are going to be equal. Okay. So now we're going to combine sort of these polynomials as a generating function. So we're going to write down Z hat, and we're going to write down that A1 to remember the fact that we're working over FPT. Okay, so an important property of this Z hat, this generating function, is that we have some kind of product. So when I first looked at it, it somehow reminded me of Euler product, but I mean, I don't know. I mean, you can somehow philosophize that way, but it's just really the proof really is about just a smart use of orbit stabilizers. Okay, so and this was due to Stone. Maybe I should have written it somewhere here. This was due to Richard Stone. And let me think. And the second one is that, so I'm just going to define this notation where instead of looking at the whole product, I just look at the one of them, 1p, and then I'm just going to remember one factor, and then I'm just going to write it this way. Once you do that, a quick property that you can, yeah, what was the question?
Could you say again can you go back one slide? I think I missed this, but maybe you said, what is this?
No,
how should I think of this X sub H again?
So X sub H, okay. X sub H is going to be a formal variable for each finite p torsion FPT module.
Okay, there's one for each, so it's this
one for, yeah, up to isomorphism. So yeah, so for each isomorphism class of finite abelian p torsion module, yeah, you'll have one. Yeah.
And there are no relations. Okay.
There are no relations, right? Unless it is 0, which you call it 1. It's not going to be a variable, right? So again, like, yeah, that's it really. So in more practical word, this is going to remember a partition and a p, the polynomial p.
Mhm.
Are there any other questions?
And is there a reason the name it's called cycle index? Is there?
Yeah, there is a reason for it. So you can do this for GLN just by forgetting the polynomial t, and there was a version for it for group Sn, symmetric group Sn, and there it was called cycle index for a long time because there, I mean, in this case, this remembers the conjugacy classes of the matrices, and their conjugacy classes of Sn is exactly the cycles. So I think that's I actually didn't ask people who invented this, but I think that's probably why they call this cycle index.
Thank you.
Yeah, and this classically, that cycle index for Sn was used in sort of combinatorial theorem called Polyanimation Theorems. Okay, so where was I? Yeah, so I was defining these notations, right, for A1 and P, and then I didn't technically define these notations, but hopefully this is clear. So if you look at the property 1, all I'm saying is that, well, because it is some sort of, this d hat is given by some sort of product, you can somehow, like multiply, like you can somehow like not multiply each sum of the points and then multiply it later. That's all that says. And then the second one is more interesting. The second one is that if you don't do the first one, if you don't multiply the polynomial t, and then plug in 1 everywhere in x, then what you're going to get is a 1 plus u squared plus etc. 1 over u. So that's going to be 1 over 1 minus u. Okay, and the reason is this. The reason is that, let's go back to the slides. Hopefully this is not too confusing. When you look at each coefficient, okay, when you look at each coefficient, what you see is that you're averaging over GLN. Okay, so if you forget about that polynomial p being t, what you're going to see is the only GLN. And then if you plug in 1 everywhere, you're just this polynomial will become 1. So if you make a generating function, each coefficient is 1, so you get 1 u squared, etc., and that's what you get. Okay, and it's very simple, but it's good. This is also important in the computation. Okay, this is what happens. And what's the most important part of this computation is the result of Stone, is that if you just look at the one factor for one polynomial p and then plug in 1 everywhere, okay, that expression, whatever that is, it's going to look like this. It's going to look like what's on the right hand side. So this, again, this wasn't, I don't know, like this wasn't using like any heavy theory or whatever, but it is a nice, neat computation. And then all the proofs that I know relies on counting how many n by n nilpotent matrices are there, which is famously known as a Fine-Hurston theorem. Okay. So these are going to be the properties that I'm going to use for counting matrices over a finite field. And there's one more thing that maybe this might annoy some analytic number theorists here, because it's such a simple theorem, and then calling it Tauberian theorem. So what it says is this. So if you have some sort of power series of power series in U, that's f of u and then g of u, and then somehow if you have f of u being equal to g of u, divide by 1 minus u, then what happens is that if you compute the limit of the coefficient of f of u, then it becomes exactly the same thing as a plugging in 1 in G. Okay, that's all it says. So we're gonna just see this in a, and the proof is extremely simple. You just like, instead of 1 over 1 minus u, you just take it to be 1 plus u squared, etc., etc., and then you just match the coefficients. Okay, but this is important in the computation. So let's hope that we're remembering these things, and then let's move to the computation. So, and I'm only gonna sketch it. So if you follow, it's great. If you don't follow, that's all right too. So what we do is that we just literally like just have some choices about what to plug into to x, the variables x, and then the first thing you do is that you sort of separate some how do I say this, some points or some polynomials p1 through pr, and then like and then for those points you don't evaluate, but for the points, for the things that you took out, you just evaluate to be 1. Okay, and then what do? Instead of subtracting these p1 through pr, you can just divide these factors just based on like what you see from the definition. Definition of z hat was given by multiplying through all p's. Okay, so you can just divide by them instead of subtracting, instead of not thinking about those p's. And then so what you have is this thing where in the numerator you have z hat of a1, but you can just rewrite it. You write it as a z hat of a1 minus t and then t. Okay. The reason why I would like to do this is because the first part is going to be something that we saw before, which is 1 over 1 minus u. And then you have something remaining here, right? We have something remaining here. But then if you recall this combinatorial Tauberian theorem, and if you go back and if you think about it, what we're going to do, what we are interested in is basically taking some limit of the coefficient of the left-hand side, modulo the fact that we're dividing by GLN instead of mat n, but that can be resolved because we know exactly how to count GLN. So what we do is that we just multiply that factor to correct that denominator, and then just plug in 1 there, and that's it. Okay, and then that's the proof of this. I mean, it looks complicated, but that's like what I explained is basically how you get the proof. I'm actually surprised that I got through this far. Are there any questions? If yes, I can answer, and if not, I can explain. I can advertise our conjecture that we got stuck on. Okay. 3 seconds. Yeah.
So I have a question.
Yeah.
So this cycle index technique seems very interesting. Can you give an example of what's the simplest problem that you know of where this is useful?
That's actually a great question. I feel like the simplest problem is this in some sense. As in like you literally know information about the p parts of the of each matrix. So I mean, so for example, what can you compute? If you know p part, you know a lot of things, right? Just yeah. Sorry, I can't quite. Yeah, but all I can say is that if you're somehow like get stuck on counting certain kinds of matrices with algebraic condition, try to use this. This is all I can say, Frank.
Okay, thank you.
Yeah.
Can I ask maybe a related question? So so this construction was like at the beginning to make this generating function, it was purely formal. Take a formal variable x sub h for each what was this isomorphism class?
Yeah, correct. Yeah, let's Yeah, so it was
okay.
it was this thing, and then we just take the generating function for this, right?
Do you get and the main application of this for us was counting, well, no. So it was like, okay, now I have to jump back to your other slide. So
Yeah. So those
you get, I was
so
I'm wondering
matrices
if
with
you can,
certain
I'm sorry,
matrices
I'm still,
with certain p parts. So that's basically what we're computing.
my question is, do you get to say more things if we impose some other natural relations to impose in these variables that let you
I see. Yeah, that's a good.
let you count something else? I don't know. I've
Yeah,
like
that's a good question, and I think I think one can try a lot of things. And what we're counting is very sort of inbuilt in this construction. So for us, all we had to do is to plug in 1 and zeros in X. But yeah, I can imagine you can probably, like, depending on how you use it, maybe you have maybe more some sophisticated way, although the way to resolve your problem might be a lot more complicated depending on your problem. Yeah, I mean, of course you can do a lot of things. Yeah, but it's just that maybe computation might not be so simple even if you try that.
All right, thanks.
Yeah, no problem. Yeah, it's just this, like, like you just encode these things that you want to count and make into generating function. You have some sort of infinite product formula, and then you should look at left hand side and right hand side. Somehow things happen. I think that's sort of the moral of the story for this finite field.
Yeah, I was going to say something like, you're not quite like getting heuristics for class groups of imaginary quadratic fields in the finite. You're doing some hybrid problem, which is not quite FPT. It's not quite.
No. This is again, our interest was just to think about the computational problems for random matrices over ZP, and then we sort of reduced that to, and motivation came from such class group problems, but like we're not doing those class group problems at all. No. Yeah.
But you could go back. So okay, you couldn't go back to the Ellenberg Venkatesh stuff, but you could say something about the Friedman-Washington calculations. You recovered some.
Yes, but those calculations were about ZP matrices. They were not about the. So yeah, because we don't know that these class groups follows like the Haar measure type of stuff. So yeah. So I mean, so yeah, when we started this, like maybe we sort of dreamed about maybe we can contribute to something, but as you get more used to this problem, there's no way. Like I think it's just yeah. But I mean, maybe you might start with the problem that actually where Haar measure is embedded to your problem, then yes, then that's, yeah, then the techniques like this might be helpful. But for class group problems, what's really difficult is that it seems like how to even parameterize in the beginning. So you don't even know where to begin somehow, or at least that's my take. I mean, I'm not an expert in doing that.
By the way, I have chat.
Yeah, there's something in the chat. Oh yeah, there are a bunch of there's a bunch of suggestions by my collaborator. Yeah, I think yeah. I see. I mean, some of these things are what we're thinking about, so I don't know. But anyways, okay. So any more questions? Otherwise, I can share our conjecture. So remember that somehow we have this petty sort of conditions about lots of co-kernels having to be 0, and this only interesting part of this push forward of that by the polynomial, that polynomial had to be degree 1. Okay, so like our conjecture is like what happens if we don't impose any of these conditions. Of course, like we don't know how to do them, but let me share the conjecture with you guys. Okay, Okay, not thank you yet, but okay. So in order to formulate the conjecture, I'm just gonna set up some notation, but this is not going to be hard notations if you have been following so far. So let's just like for any prime power p and a integer partition lambda, where lambda consists of these L numbers from L integers from lambda 1 through lambda L. I'm gonna denote this weight WQ lambda to be the size of the automorphism group of the following P torsion FQT modules. Okay, so Q might not be a prime. Okay, it could be a prime power as well. Okay, and for finite abelian P group with H, I'm just gonna call lambda H to be the corresponding partition of that. Okay, so with that in mind, so let me formulate our conjecture. Our conjecture is that it's the same sort of type of scenario where you have finitely many monic polynomials over ZP, and that reduces to, again, sorry, distinct irreducible polynomials over mod P. And if you have finite abelian P groups, if you try to sort of match these co-kernels with them, we conjecture that it's going to converge to that quantity. Instead of that automorphism, the size of the automorphism, you have to have these weights instead. But then we expect these to be normalizing factors to be the same. The reason why we have to use this is that if we don't use this, if we just use the sort of the good old the size of the automorphisms for finite abelian groups, finite abelian P groups, then our probability don't add up to 1. Okay, so that's why we don't necessarily we don't know that whether or not any of this is true, but we accept what we have proven. But this is what we conjecture. So I mean, if you might want to try it. We had really hard time even for when we have one polynomial with degree 2. We don't know how to do it. Okay, so if you're undergrad, you could just, you have great computer skills, we can disprove our conjecture. We haven't really tried much that either. So that's it. Sorry for going over 1 minute. Thank you for your attention.
Okay, great, thank you. Let's give Gilyoung a virtual round of applause. I think there are these little applause icons. Okay, so we have time for maybe a couple more questions or comments. Anything? I guess maybe everybody asked their questions already. Okay, well if not, then let's thank our speaker again.